Hi everyone! In today's video we're covering recursion and we're going over a few examples including using tic-tac-toe between me and Matt, and we're also going to be covering the difference between recursion and iteration and talking about the recursive and iterative implementation of depth-first search. I hope you guys enjoy the video. Let's get into it. So what is recursion? A recursive function will call itself repeatedly, and a function will continue to call itself until a base case is met. Okay. It allows problems to be split into smaller subproblems using this recursion, and it can be used in decrease and conquer, which we've covered in Unit 3, and divide and conquer, which we will cover in Unit 4, algorithm designs. So let's have a look at this recursive function here. So if the base case is met, we return the input. So this is our base case, and it ends the recursive loop. Otherwise, it's going to do a recursive call and start the function over, and it could do more than one recursive call. So we can think of recursion as a stack. To understand how it's processed, we can visualize it this way. Each recursive call adds another layer to the stack, and each return or base case will remove that layer. If the stack gets too high, the stack can overflow. So we've got the function here. If the base case is met, this is the same function as before. So while it's doing the recursion before it meets the base case, it's stacking up. And then if the base case is met, it goes back down until it finishes. Recursion versus iteration. Both of these are a type of repetition in algorithm design, and they can both be used for a decrease and conquer algorithm design. Recursion uses functions that call itself, whereas iteration uses just a loop. So this could be a while loop, a for loop, different kinds of loops. This is an example of the same algorithm, completed recursively and iteratively. So you can see the recursive one might look a bit more complicated. It's adding a total up until it reaches 5. And you can see the base case in this case looks a little bit different. While the other one, the while statement itself, has a sort of base case embedded in it, where until it reaches 5, it'll just stop the loop. Whereas the other one, we have to do a check for that, and then for that check, we can either continue recursively calling the function, or we can end it. So you can see here, here's the loop, and here's the loop where it calls itself again. Same thing. So why use recursion? In this example, it looks a bit more clunky. Well, we'll learn that it has some things that iteration can't do as easily, and it can decrease complication in that aspect. So, Matt and I have been playing tic-tac-toe.
Ooh, nice play. I think I have you outdone. Oh, it's getting close.
I don't know what to do now. I've decided, this is our board so far, I've decided to cheat and see all the possible outcomes, and how would I solve this recursively? So we're going to write a bit of an algorithm using recursion to have a look at how I would do this. So in this case, what's the base case? Well, the base case is going to be what ends the recursive loop, and I would say it could be when someone wins, then we don't need to keep playing, we can end the loop there. Or it could be when all the squares are filled, because then the game's ended, we've tied, if someone hasn't won. So what information does each recursion need? So if we're thinking about the board, and let's say where each recursion is going to show a different move that could be made, then what does each recursion need? Well, it's going to need the current board, and it's going to need whose turn it is, X or O, and it's also going to need what move is being made. So maybe I'm making a move in square 1, could be in square 2, there's different ways to visualize that information. That's not what we're worried about today, just more so the recursion itself. And what is going to be returned at the end? Well, in this case, it's going to be the ending board. And maybe every possible ending board, so I can see all of the different outcomes, so I know which move to make. So this is the function that we've done. So it works like this. We've got add turn to board in position. So it's going to start with the board, what turn is being made, and what position the turn is being made into. So we're adding turns, that could be X or O, onto the board in that position. So if we're representing the board as a list, the position could be like 0, 1, 2, 3, 4, 5, 6, 7, 8. If the board is full, or there's 3 in a row, then we can return the board. That's our base case. All done. And then otherwise, if it's O's turn, then we're changing it to X's turn. Else the turn's O's turn. So we need to make sure we're changing whose turn it is. We're gonna update all of the boards. And then for each empty square, we can call the function again. So we're doing this for every empty square. In this case, it's 3 empty squares, so we're going to make 3 calls. And it's going to append all of the boards into that boards list. So that's essentially what we're doing. We're going to call it for each empty square that there is. So let's have a look at how this would work. This is our board right now. So the first call it's going to make, we're putting X in the first position because it's X's turn. And then one move that could be made is 3 X's in a row because O's gone over in that corner there. And that's a base case. We can go back. Or X and O could go in this way and it's a tie. That's also a base case. Alternatively, if I put X in the bottom corner down there, then maybe Matt wins. That's a base case. Or maybe Matt chooses not to do 3 in a row, and that's also a base case. And then maybe I put X in the bottom, and then Matt still does 3 in a row. Or he could not do that, and I could get 3 in a row. So there's a few different options here. Now, if I'm playing as X, I'm probably going to go for the first option, because I'm blocking Matt from possibly winning the game. There's no possible way for him to win if I do that. There's a possible way for me to win, but it does rely on Matt choosing not to block my move, which is kind of unlikely. I'm gonna win this.
How could you do this to me? And there we go. It's a tie.
Good game, good game, good game, good game. So why recursion? Think about our last example. How would you implement that with iteration? If we're thinking about the stack, we can stack up and down as needed when exploring different branches of the solutions. So you see I'm stacking back down because of the different recursions. If we think of the last one, I'm calling down this path and then branching back down this path. So then I'm branching back down a different path. So let's say I explore all the moves on this branch, and then I explore all the moves on this branch, and then I explore all the moves on this branch. What algorithm does that remind you of? Depth first search. Now this is going to be something to point out. We've covered depth first search before, but you're probably more familiar with the iterative version, which, is looking quite long and clunky here, kind of hard to understand. Now look at the recursive version. Does exactly the same thing, but it's so much shorter. Now you can view this whenever you want, and it's also on the LMS. But which solution do you think looks easier? I hope everyone enjoyed the video on recursion. Today we looked at a few examples, the difference between recursion and iteration, and we went over depth first search. If you've got any more questions, feel free to reach out to Georgia. I hope you guys enjoyed the video.